Hello, Dr. Sophie and June again, and we're here to cover concepts of the Wheatstone Bridge. So Dr. June is going to start talking about the general concepts of the Wheatstone Bridge.
So this is the circuit diagram for a Wheatstone bridge. In general, we have 1, 2, 3, 4 resistors arranged in a so-called bridge fashion. There are at least two interesting points to measure the voltage in a circuit like this. The first is what's called Vs, the source or the input voltage, and that is denoted with appropriate polarity here. The second is the voltage between these two nodes here, and that's denoted the output voltage of the bridge. So the Wheatstone bridge is a valuable tool for engineers to convert a signal that changes with resistance into a voltage signal, which we all know can be measured by DAC systems. And so the most important equation for the Wheatstone bridge is the general equation, which is shown down here, which holds even when V naught is not 0. So when V naught is not 0, we can say that V naught equals Vs times the quantity R2 over R1 plus R2 minus R4 over R3 plus R4. And quantity. Again, V naught equals Vs times this big quantity R2 over the sum of R1 plus R2 minus R4 over the sum of R3 plus R4. So you can see here that if you need to increase the magnitude of your output voltage, what you do is you apply a higher source voltage, assuming you're not going to melt your resistors. Now Dr. Sophie is going to talk about what happens when we can balance our bridge, which means that we're going to make this V naught 0.
Now it's a little bit more tricky when your no voltage is not 0, but in specialized circuits where we can hold the no voltage to 0, a much more simplified version of our resistance balance becomes effective. So for a no balance bridge, which is the basis of this first lab that you're going to be doing, we're always going to set V naught to 0. And so R1 and R3 are fixed resistors, R2 is a variable resistor, and R4 is your RTD. And the basis of how this is going to work is that R4 is going to change its value, and we are going to adjust R2 manually on a resistor decade box to make sure that our no voltage is 0. So we're going to be directly measuring our no voltage via a multimeter, and when we calculate, or when we make R2 achieve a no voltage, then this simple equation comes into play that R1 over R2 is equal to R3 over R4. So basically that leg is equivalent to this leg. And mathematically it can be R1 over R3 is equal to R2 over R4. But what's really important about this is, remember, R1 and R3 are fixed. This one we are adjusting, and we know what value it is. And once we have that, we have one unknown. And we can calculate the resistance of R4, and that resistance is going to correlate to a very specific temperature value that's cited through an equation that we can use from the manufacturer.
That's it for Introduction to Bridge Circuits. Thank you.